recurrent neural networks. And then if you remember vividly, we said it is ideal for sequential time series kind of data, speech recognition, natural language processing, and forecasting. Now, one of the things that gave it advantage was because of the feedback loop and also the memory cells that it has that helps it to be able to retain information, and regurgitate it a kind of. So we said the use cases have like Google Translate, Siri, Alexa, stock prediction, and so on. Now, if you look at the architecture, you will also see it has the hidden state. It has this attention phase where, it's, give certain sentence more weight than the other previous ones. So like if we said, I am pleased, it will focus more weight on I am pleased. It's so bad, something like bad. So this will carry more attention than maybe is or something. But how it does, it will break them into these tokens. That is what we call tokenization in natural language processing. Let's see how far we go if I could tell you guys about that. So it breaks them into these tokens and creates some sort of future matrix that each of these words will now be given a weight. Then the same way like you saw from the convolutional neural network, it has this different state that it will pass through and carry out all those transformations. But there is the attention representation and the global representation, where in the attention, it will put max pooling of the the whole thing will happen at the global phase, where it will now looks at what it has compiled from the attention phase, and then at the end of the day, it gets to the global phase, and then all of them will continue to move up until when you get to the final phase where you output it, when it's being acted upon by sort of a soft matrix. Then we also say that one of the advantage of the recurrent neural network is the back propagation through time. That it goes back each time it loops and updates the weight. When you run it, it updates the weight through that back propagation. So, but another thing, if you remember, I said it supports one to many, many to one, many to many input output. Like I said in ChatGPT, and I remember I gave you guys one example where we said write a poem or something, and each time we give it to the different ChatGPT and even the same large language model, you see that at each return, it doesn't return the exact information. So each time you look, it gives you a different answer. So because of the way the neural network process the information. However, we said that the recurrent neural network has a limitation. Because of the limitation, there are issues when you begin to have long sentences or longer phrase. It begins to misbehave because it couldn't really be able to regurgitate it very well. So that gave rise to things like long short-term memory. So the long short-term memory was able to handle these long-term dependency issues better than the recurrent neural network was able to do. So the advantage is the fact that yes, it will handle sequence dependency, and also useful when you have the temporal context in it, especially when you are looking at things that has to do like geolocations or some sort of time incorporated into the data and maybe locational data, then the recurrent neural network can handle it like the way the LSTM can. However, one of the problems is vanishing or exploding gradient. Like I told you guys that remember these things do back propagation, and the back propagation operates in form of chain rule because you are coming back. So because you are coming back, if you don't optimize it or minimize it very well, you can easily have a very small value that can easily go to zero and vanish. And at some point, you can also have a very big value that moves towards infinity and is exploded. So it is quite slow sometimes to train. remember it's holding information in the memory cell. So you could imagine when you have lots of information, it gets to a place where it easily gets, they require a lot of memory. So it's complex to optimize when you have a lot of layers. So we also have other like autoencoder, birational autoencoder, and all that, which is not what we are going to talk about today. So we are still focusing on the recurrent neural network, and also specifically we wanted to look at the LSTM. We say the LSTM is a special variant of the RNN because it's handled the long sequence dependency challenge quite well. So a cell state serving as long term or memory, and also it has these three gating mechanisms. So what those guys did was to introduce these gates, that it has the input gate, the forget gate, and the output gate. So these gates learn when to write, retain, or discard information. Then the architecture is designed in such a way that it could be able to manage vanishing gradients and enable the model to handle long-range dependency in sequence data. So what the forget gate does is that it determines how much previous cells the cell state need to retain information. So if that information is not important, it will discard it. And then the input gate, on the other hand, or the candidate update, it decide on what kind of information it should write. So if the information is important, it will write it in the input. Remember, the input stage is like taking one information from one layer to the other, while the output gate, on the other hand, control the part of the cell state to output. So it's not all the information that you give it that it's going to come out. It will look at how important it is. Should it forget it, or should it process it? By the time you do that, then it will move it to the output gate, which will now uh, be the one to output it. So together, they dynamically control the memory flow, enable the network to hold onto useful past context while discarding noise. Then when are you supposed to use this LSTM? When you have time series forecasting like stock prices or weather. It's very, very active in this area. And then natural language processing. When you are dealing with natural language processing, it's very, very good, especially like text generation or translation. Audio to speech recognition also is very good in that area. Music compositions, users' behavior prediction, etc. So most of the time, when you are having sequences like sequential data, then it's really, really good to put the LSTM into consideration. There is implementation of this LSTM in TensorFlow and Keras. Now, when we say TensorFlow and Keras, they are the packages we use from pep install in Python that we use to handle things that has to do with deep neural networks. Then in this hands-on section, we're just going to focus on the LSTM, but feel free on your own path to explore the recurrent neural network itself, and then you could be able to see what it can and what it cannot do. And then I'll also give you guys a link to a reading material. I think from this guy, I used to read most of the materials he posts. I think one of his subscriber. He talks about machine learning mastery. Most times he puts a lot of very useful information. Johnson Browsey or something was like Brownlee. He put a lot of information on different topics. Sometimes during the week when I'm reading, I just pull some of his information to read. So I could give you guys the link where you could further explore some of the materials that he do post. live information from there. All right. So we said that in this class, one of the things that we are trying to look at is how do you process sequential data? How do you define the LSTM units, the return sequence, the layer, and then how do you compile to the optimizer loss during the training, like we saw from our previous class in convolutional network. Like I said, if you haven't watched the video, try to watch them so you could be able to keep track of the classes. Then to evaluate and also to generate prediction on new data. Remember, even if it's deep learning or normal traditional machine learning, all what we are doing is still going to be training, testing, validation. So it's always, within these three phases. So the first learning objective is for you to be able to understand the limitation of the traditional recurrent neural network, which we have talked about. It doesn't handle the long dependency. It has issues whenever you have long sequence. And also, we want you to be able to explain the internal architecture of the LSTM. Remember the forget gate, the input gate, and the output gate. Then we also have to identify use this when it's effective. Remember, we mentioned just now that it is very effective in stock prices prediction. It's also very effective in weather, and also other areas that you can be able to that has to do with geospatial sort of statistics. It's very effective in these areas, and then you can be able to implement it in Tensor, Keras, Python kind of scenario. So the first thing we are going to do in this class, we are going to load most the important packages or libraries we are going to be needing. Remember Matplotlib for visualization, NumPy and Pandas. We use them for data manipulation and also loading data. And then we also have the scaling, like the min, max, scala. We have the training test splits that comes from sklearn. And we also have the TensorFlow from Keras that helps us with the sequential part. And also we have the TensorFlow.keras where we load the LSTM and also the DEMS and dropout. So let's quickly load these libraries. We have done that effectively. So remember, if you have, like I said again, if you watch our last video, you will see how you can be able to effectively get the Google Colab. So if you are right now working on your laptop, you could quickly look for the Google Colab. I said once you are in your email, you quickly come to this part of the email, the drive. Most times this is where you'll be able to save all your scripts that you are working on. It's all going to be saved on the Google Colab drive. Sorry, on your Gmail drive. Most times you see all the information that you need. So if you have not yet understood how to do that, I think in the previous class you can see how I divulge, I think, up to 10 minutes talking about it. So you could follow on it and see how you can be able to, yes, yes, yes. Oh, okay. I think the code from last week was in our GitHub repo, but at the end of this class, I will send the code and the slides to the group so you guys could follow. But I've already put it on GitHub, so each time you can just go to our GitHub and pull it. Once you come to this, you could just type our GitHub repo. So once you load, no, Google Colab, sorry. Yeah, so once you come on GitHub, you will be able to see learning Once you come here, I put all the code and even the slide, I put all of them here on GitHub. So once you need any scripts, you can feel free to pull it out from GitHub. I think if I'm not mistaken, the neural networks, I put the script here. I'm not mistaken. One of them. Yes, this is the script from last week. So you'll always feel free to, but I'll still send it to you guys at the end of the class. All right. So once you upload the library, the libraries from the packages, the next thing is we need to import a data set. Now, the data set we are using is a data set on milk production. It's a data set from milk production where we have now let's look at the data. So this is the production in from 1962. I think we can also look at the tail of the data to see data the tail to see what year it ended. Yeah. So down to I think 1975. So each of them, you see the quantity of the milk that was produced in each of this year. So we would like to so that's the time series data, because when you look at it, 1962, January, February, March, you can see from each month the quantity of milk that was produced. So, but then again, when you look at this data here, you need to convert it to the date format. So the PD to date time help you to be able to convert time series, the data to time series. So once you run it, it has converted to time series data for you. So the next thing we are going to do is also to reshape the production data to around to have a sort of a, when you are working with times with convolutional neural network, you need to make sure you put the data on the right. If you remember when we were talking about convolutional neural network last week, you could see us trying to downsize, resize, and all that. All is to make sure we fit that data to the right format before feeding it to the model. So that's also what we are doing here. We make sure we reshape the value of the data before we feed it to the right framework. However, prior to that, we need to do some exploratory data analysis just to know what we have, looking at the data type. So the data was not big because I don't always want to keep us for a long time, these things running. Since these are just random section, you just open your eyes on what you can be able to do, then you could explore. So most times I try to minimize the complexity so we don't have to, because we are managing some of our memories, so we don't want us to keep a lot of time running these things. Then we can also look at some descriptive statistics. So the data was 168 samples, and we only have one column. So if you look at again, this data looks more like quantity. So it's going to be a regression problem, not a classification problem. So take note of that. So when you run the descriptive statistics, you'll see that the count is 168. The mean is around 755 approximately. Then the standard deviation around 102.2, and the mean is around, the minimum is around 553. Then the 25% percentile or something is 677, 6778. Then 50th% or median, it's around 761. Then the 75 is 825, and then 969 for the maximum. So we would like to see the line plot of the milk production over this period of time. Remember, this is a time series data, so it makes sense if you can visualize it to see how the data moves in the process of time. So good. So you can see how the data moves in the process of time. You can see this zigzag movement, peaks, moves up and peaks here, and then it comes down, peak a bit here, move up, peak like that. So you could see the sequential movement of the data. Now, it will make sense also if we are able to plot the the rolling statistics. That's the mean around the standard deviation for as the data is moving, to see what happens. So, but funny enough, you see that the rolling standard deviation is very small, which is fine. You don't expect it, of course, to go up. And then the original data is the one here. And then we see how the mean is increasing also over the period of time. It also makes sense. Then it will make sense to look at the seasonal composition because this is a time series data. So most times you look at all the variational changes, the peak and off peaks and all that to help you to be able to make right judgment. So if you look at the seasonal decomposition of the production using additive model of, and then the period from 12 in time series, I think we used to do a lot of this when we were looking at Sarina, Arena models. If you know your statistics, you remember them. So you looked at that, looking at the period of the decomposition, you could also see the way the trend goes over time. Now, the seasonal variation as well, you could see it's actually kind of very stable. And then the residue as well, you could see how uh, you should look at these things. So it do make sense for me. I think it's fine. Then the next thing we just want to do some histogram to see how the distribution of the production will look like. And yeah, we did have quite not really normal. I think it's some sort of a bit of flat sort of distribution, but we could see in general it's actually nice. With some certain extent, it looks the curve was not that bad. The it's not really more. It's quite just a bit of high around 800. Then next is to begin to prepare the data for modeling. And for you to do that, you need to first scale the data, which is what we just did now. And then the next thing you need to create the training test split. Now, when you look at from all the plots we have, it makes sense for us to maintain the window size of 12. From all the exploration, we see that the seasonal variation is around 12. But some people can say they will use 6. Again, it's totally choice, but the window of 12 is fine, I could say. So we could select 12, and then remember we are going to split it into 80% training and 20% testing. So once you run this, now the next thing is for us to build the LSTM model architecture. So in this step, like we said, what we are looking at is we are building a model that consists of 2 LSTM layers. Like I said, these are examples. There is no need of making it complex. Now, each with 128 units and a dropout after each to prevent overheating. the model concludes with a dense layer to predict a single value. That's next month's production. So we want to remember we are looking at the milk production each year. So it makes sense if you want to predict for the subsequent year, so you can be able to know. For example, now, for somebody who is interested in agricultural research or a farmer who wants to know the milk production of his cattle, and that would be able to help them to be able to know what is happening. Because if you can imagine some of this milk, you have to supply to some of the processing plants and all that. If you know the production, it helps you to plan your supplies and demands very well. So that's what we are trying to understand with this model. So by the time we define, so the model, like I say, it's sequential because of the ups and downs, and then we are looking at two layers. So this is the first layer which we define, and then this is the second layer, which is no, this is the dropout for the first layer, and then this is the second layer, and then this is the dropout for the second layer. So what we are, this 0.2 means we should drop 20% of those nodes that we noticed they are not contributing, or memory cells that are not, we should just remove them, and all that. It helps us during training. Then the optimizer we are using is ADAM. The ADAM optimizer is the most popular ones. There are other ones, but ADAM seems to be much more popular. I don't really have time to go into telling you all this nitty-gritty, but you could explore the ADAM optimizer and other optimizers we have to see what they do. But the ADAM optimizer is much popular among the other ones. So during training and evaluation, we are going to use 100 epoch using a batch size of 32, with 10% of the training used for validation. After training, the model is used to make prediction on the tested, and we will calculate the root mean square to evaluate. So remember I said in regression, we are using the root mean square or the mean square error. It's one of them that we use this for regression problem. But when we are talking of classification, that's when we begin to look at accuracy, F1 score, precision, and so on and so forth. But remember when we talk about the root mean square error, the smaller the better. So most times we don't want large error, because once there is large error, we can know that there is overfitting. So we are always, and another thing again, if you notice, we have 100 epochs. Why? Because our data is not that big. Our data is very small. So it makes sense if you have 100 epochs, so that the model could be able to really look through to, really like explore the data very well. But if our data is very large, it doesn't make sense for us to have this large epoch size. So depending on how big our data is, will determine the kind of size of the epoch we want to create. So now you can see as it's running, we can actually see the first run, but we can start see a sort of decrease in the loss, and the validation loss too was kind of decreasing. So we can start see at some point there seems to be like some sort of overfitting. But now when you begin to go down, you see that it's beginning to make sense, balancing themselves out. And then finally, it has finished training. So let's see what we had final loss. So we had around 0.0054, and the validation loss was 0.0045. And then we had the root mean square to be 29.09. Now let's visualize and see what we have. So when you visualize this, you will now see that so this is the actual production, and this is the predicted production. So let's see if it makes sense. So you can actually see the actual production and the predicted production. Of course, we don't expect this close when it's too close, right? Definitely, we're going to know that that's an overfitting. But you can actually see to a large extent our model is able to still be able to follow the same patterns that the actual production was following. Even though, yes, we could see it was not able to pick this middle here, for both of them, but we could actually see it was able to get right from all these other parts. So that makes us to understand that our model is actually doing well. It's not really doing bad. So there are other examples I would have loved us to explore, but again, the one of the example of the LSTM that I'm using currently, it's kind of data intensive, so that's why I didn't share with you guys. And that one is still on this networks that I'm building. But I didn't care to share with you guys that example, because it's quite going to take us a lot of time running it. But this is just a small example of how you could be able to run the LSTM